Welcome to Lecture 4 of Introduction to Quantum Field Theory. In this lecture, I'll continue to explore the way that quantum mechanics can be written as a path integral. Again, the reference for this particular lecture is the textbook by Leine and Vuorinen, Basics of Thermal Field Theory, Chapter 1. In Lecture 3, we found an expression for the quantum mechanical partition function that was written as a high-dimensional integral over both position space and momentum space of a single exponential. The only restriction of these integrals was that the position space with label 1, x1, had to be identified with the position space at label xn plus 1, so the last insertion of this position space indices. This just means that in terms of position space, we sort of are looking at periodic boundary conditions. We can actually think of these different insertions of the position space, x1, x2, x3, and so on, just as points on a line, okay? The spacing in between those is given by the spacing in between the different x values, and that was just given by our discrete parameter epsilon, which was the inverse temperature beta divided by the number of points that we have, n. We can think of this line of points as just being a discretized version of a continuous coordinate tau. Put differently, if we think of a line that's being parameterized by the coordinate tau, then the points that we've been talking about before are the discretized versions of tau equal j times epsilon or j times beta over n. And because j runs from 1 to n, that means that tau runs from beta over n all the way to beta. Now recall that I said that the first point x1 had to be identified with the last point. In terms of the continuous time coordinate tau, this just means that x of 0 is equal to x of beta, and the line closes onto itself. Since this circle that we get here has a circumference of length beta, which is the inverse temperature, this circle here is called the thermal circle. In the limit where we take the number of insertions n to infinity, the new coordinate tau becomes continuous, and it ranges in between 0 and beta. For reasons that only will become clear later on, we will refer to this coordinate tau as imaginary time. Using tau, we can give continuum meaning to these discretized expressions that appeared in the partition function equation 4.1 above. In particular, I draw your attention to this difference xj plus 1 minus xj of epsilon that will turn into a derivative, and the sum j0 to n times epsilon, which will appear as an integral. So this is sort of the formal continuum limit of this difference. It's just the derivative of x now as a continuous function of tau, derivative with respect to tau, and the sum here becoming integral from 0 to beta d tau. All the position space entries as well as the momentum space entries will then take on a continuous form such that instead of writing x index I, we'll write x as a function of tau, where tau basically sort of replaces the discrete label I. Using this imaginary time coordinate, the partition function then can be compactly written in the following form. It's still an integral over an exponential. The exponential now involves an integral over the tau instead of a sum. And instead of involving a difference, it involves the derivative of the coordinate x of tau with respect to tau. The integrals that we had in the measure here basically sort of are written in terms of this calligraphic dx and dp here, where the meaning of these calligraphic symbols really sort of is the limit n to infinity of the product I is 1 to n of these individual integrals divided by 2 pi. The expression where we take tau to be continuous is referred to as the continuum path integral. This continuous expression for the path integral contains a path integration over two functions, the position and the momentum. Since in this lecture we consider only Hamiltonians where the potential v of x is independent of the momentum, it is possible to integrate out the momentum, and we get a simpler expression for the path integral. To do that, it's most convenient to return to the discretized version of the path integral. So if you look back at formula 4.1, that was the start of today's lecture, you'll find that the momentum integrals actually factorize, and they are all of the form here, where we have a momentum integral times a Gaussian, essentially. We can integrate out the momenta pi, and we get the right-hand side here. If we do that with all of them, then we find that the path integral here becomes the limit n is infinity of just the integration over the position space variables x times a different measure times an exponential. And this concludes today's lecture.